So far we've taken the derivative of a function and we've used it to find the slope of a function f at a point, and we've also used it to give a rate of change of the function with respect to x. And there are many real-life applications of rates of change. A few of them are like velocity, acceleration, population growth rates, unemployment rates, water flow rates, and often rates of change involve change with respect to time, but you can investigate a rate of change of one variable with respect to any other related variable. So it doesn't have to just be time. Let's take a look at average rate of change. So the average rate of change of y with respect to x on the interval. So let's just draw a little curve here. Let's say we have this curve, and this will be the x value of a, and the function is f, so the y value will be f of a. And then we'll go over to the right a little bit. We'll pick a new point, and this point will be b. So therefore, the y value will be f of b. Okay, so we're looking for the average rate of change then. We are once again looking at the slope. So the rise is going to be f of b minus f of a, and then the run is going to be b minus a. So notice on this, the b is the point that's to the right of a. Okay, so this is just our formula for slope. So that should look very familiar, because that's how we find the slope, and that is your average rate of change. It's important here, I have a little note to distinguish between the average rate of change and the instantaneous rate of change. So the average rate of change, you can kind of relate it back to the slope of a secant line, whereas the instantaneous is the slope of a tangent line at that point. Okay. In medicine then, here's one example where we could use rates of change. The concentration in milligrams per milliliter of a drug in a patient's bloodstream has been monitored, and you can see in this table it goes every 10 minutes for an hour and 20 minutes. And we want to find the average rate of change over each one of these intervals. Okay, so we are just finding the slope. So let's take the first 2 points here. So we want to go from 0 to 10. So the concentration is the y value, so we want the change in the concentration over the change in time. Okay, so for A, we're going from a concentration up to 2 minus, there was 0 to begin with, when the time increased 10 minutes, so we go 10 minus 0. So we get 0.2. And this is a rate of change, so remember this is 0.2 milligrams per milliliter where t is measured in minutes, so per minute is how we would put a label on that. Okay, for this one, for B, we're going from 20 to 0. So now we're comparing these two. So I want the change in the concentration. So 17 minus 0 over 20 minus 0. So 17 over 20, and when you divide that out, you'd get 0.85. Once again, milligrams per milliliter per minute. And then the last one, from 70 to 80. So the change in the concentration. So we were, when we ended, we were at 97. 10 minutes before, we were at 103. And then 80 minus 70. So here we get a negative 6/10 or a negative 0.6. Once again, milligrams per milliliter per minute. Okay, so notice here then that when it's a positive, it means that it's increasing, and when it's a negative, it means that it's decreasing. So it's important to do it. We're not going to switch the way we do the, normally when we find the slope of a line, it doesn't matter if we go x1 minus x2. But here we want to take the second one minus the first one. Always here. So the second minus the first. That way we'll know if it's positive or negative. So here we have another application, and we're looking at average velocity. Average velocity is the change in distance with respect to change in time. So I have a formula here that we're going to use, and it gives us the equation. So we've got a free falling object that was dropped from a height of 100 feet, and so this is the height of the object in time. So what we're looking for is the average velocity of the object over each interval. Well, what we have to do then is figure out what the amount is, what is the distance that it has changed. So if we want to go from 1 to 2, well, the first thing we'd have to do is figure out what the height is at each of those times. So if I plug in a 1, so negative 16, I don't know why I put a parenthesis there, 1 squared plus 100, and then we have to do it again for 2 squared. So first of all, we have to figure out what the heights are. Okay, so if you plug that in at 1 second, it's at a height of 84 feet, and at 2 seconds, it's at a height of 36. So to find the average velocity, we would take the change in the height with respect to time. So we take the second height minus the first height over the second time minus the first time, because we want it from 1 to 2. So we get a negative 48 on top, a 1 on the bottom, so it's changing at 48 feet per second. Okay, so because it's a negative, that means that it is falling, it's moving downward. All right, and then the next one, well, we have to find the height first. We already know what it is for 1 second later. It's at 84 feet, so we're going to use that again. Now we have to find the height at 1.5 seconds. And for that, you should get 64. So to find the change in the height then, we want to go from 1 to 1.5. So we take the height at 1.5 seconds, so 64, minus the height at 1 second, which was 84, over 1.5 minus 1. So we're going to get a negative 20 over a half. So we get negative 40 feet per second. Okay, so why don't you go ahead and do C here. Okay, so you can pause it for a second, and I will write down what the answer is. So if you don't want to see it right now, pause it. Should get negative 33.6 feet per second. Okay. Now let's take a look. That's average velocity. Let's take a look at the instantaneous rate of change. So we're going to take that same application that we just did, but we're going to find the velocity of the object at a time of 1. So we want the instantaneous rate of change. So we don't want the slope of the secant, we want the slope of the tangent. Well, remember we have our formal definition where we use the limit, but because we know a shortcut, I won't make you do that anymore. So to find the velocity then, we need to find the derivative. So we'd get negative 32t. And the derivative of a constant is 0, so just negative 32t. And then we want to substitute in the 1 in for the t then. So the instantaneous velocity then at time t is a negative 32 feet per second. Okay. The general position function then for a free-falling object, neglecting air resistance, is this. So you might want to write this down in your notes so you will see it occasionally. So in that formula then, the height is the h is the height in feet, the time is, the t is the time in seconds, v sub o, anytime you see a subscript of 0, that means initial. So this is initial velocity, and h sub o is the initial height. Okay, so positive velocities indicate upward motion again, and negative velocities indicate downward motion. And the derivative, then if I took the derivative of this function right up here, this guy right here, we would get this. So the derivative of this, 2 times negative 16, negative 32, t to 1 less power, and then the derivative of this is just the initial velocity. And the absolute value of the velocity is the speed of the object. All right, so using that formula, let's try this problem. So you have it written down in your notes, so we're going to go on here. So at time 0, a diver jumps from a diving board that is 32 feet high. So the diver's initial velocity is 16 feet per second. So let's do his position function then. So you're going to use that formula that I just gave you. So let's write it down in the blank here. So we have the height is equal to negative 16 t squared. And in for the v sub o, which is the initial velocity, we're going to put in 16. And in for the h sub o, which is the initial height, we're going to plug in, at time 0, he jumps from a diving board that's 32 feet high. So that'll be a plus 32. Okay, so that's his position. First of all, let's find when the diver hits the water. Okay, so when he hits the water then is when the height is 0. And we're looking for what time that is. So we take our equation. And we set it equal to 0. And then we solve it. Whoops, let me change that. That's a 32. So to factor this, let's take out a negative 16. We can get rid of that negative 16. That's never going to equal 0. Factor the quadratic that's left. So we get a time of 2 seconds, and we get a time of negative 1. Well, in this application, the negative 1 doesn't make sense, because that would mean that the diver hits the water 1 second before he jumps. So you can conclude that we just want the time of 2 seconds. Okay, so now we want to find the diver's velocity at impact. So that means at that time, when t is equal to 2, why do I keep putting that other one? When t equals 2, we want to find his velocity. So his velocity is the derivative of the position function, or the height one. So we need negative 32t plus 16. And then we can sub in the t into that expression. So negative 32 times 2 plus 16. Negative 64 plus 16 is negative 48 feet per second. So our book is more of a business calculus, so because of that we have a lot of applications in economics. So these formulas that I give you now, you're going to see that you're going to use those over and over again. So it's very important to remember these, so you might want to even highlight these in your book or put a little tab there so that you can refer back to them. So we're going to look at rates of change in economics, and those are referred to as marginals. Okay, so I have the three things that we're going to talk about the most. So profit, revenue, and cost. And the way those three things are related is that the profit is equal to the revenue minus the cost. So that formula is very important. And if we look at the rate of change of each of those, so the rate of change of the profit is the marginal profit. Okay, so do you see the derivative of the profit with respect to the number of units sold? That's our notation then for the marginal profit, and it is simply the derivative of the profit function. Marginal revenue is the rate of change of the revenue, or dr dx. And marginal cost is the rate of change of the cost. So it's the derivative of the cost function. So let's try this. We have a profit function here. For selling X units is given by this. Find the marginal profit for a production level of 50 units. Okay, so the marginal profit, we want to find the derivative. So we take our exponent 3 times 0.0002. And that goes to 1 last power. And then the derivative of 10x is 10. So if I want to find what it is for a production level of 50 units, then into the marginal profit equation, we would substitute in a 50 for the x. So we would need 0.0006 times 50 squared plus 10. And when you simplify that, I believe you'll come up with $11.50 per unit. So that's cost per unit. So it always gives you a rate when you're looking for the derivative. Okay. Now it says compared to the actual profit by increasing the production level from 50 to 51 units. Okay. So to look for the actual profit then, we would go to our profit function up here. And we want to substitute in a 50 for the x. So like production level of 50. So I'd have 0.0002 50 cubed plus 10 times 50. We want to find the same thing for 51. So the actual profit then at that point. Okay. And if you calculate both of those, you should get $525 here, and you should get $536.53 here. And so the additional profit then from going from 50 to 51 is the difference of those two. So it looks like it's 11.53. Okay. So the actual profit then, when we went from 50 to 51, we can use to approximate the marginal profit of 11.50 per unit when X is actually 50. So remember, this one then is giving us the average, so it goes between 50 and 51, where this one is the instantaneous, or the actual one right at that point. Okay, well, this example maybe isn't realistic because profit doesn't always continue to increase as long as the number of units sold increases. In practice, more often what happens that sales can only be increased by lowering the price per item, or you can make more sales if the price is a little bit lower. So usually when you do a reduction in price, then that'll cause the profit to decline because you're not bringing in as much money. So the number of, let me grab my pen. Here we go. So the number of units that consumers are willing to purchase at a given price per unit. Okay, so P is the price. Darn it. P is the price. X is how many that they are going to buy then, is given by a demand function. So the price is related to the number of units that consumers are willing to purchase. So this is the demand function. Okay. Whereas the revenue then is also related to the price per unit. So once we figure out what the X value is, what price we're going to charge, we can take that then times the number of units that will actually be sold, and that will give us our revenue. Okay, so revenue, if they don't give you the revenue equation, you might have to figure it out, and you would use it then. To figure it out, you would take the number of units times the price per unit. Doesn't that make sense? That would give you the revenue. Well, let's take a look at this. Nope, I think I went to the wrong one. I put these in a different order. Sorry, let me bring this one up. Come on. Okay, so a business sells 2,000 items per month at a price of $10 each. It is estimated the monthly sales will increase 250 units for each $25 reduction in price. So we want to find two things, the demand function and the revenue function. Well, in this particular example, you can see that it's going to be a linear function, because for every 250 units, we'll be able to sell 250 more units when the price goes down 25 cents each time. So that's going to give us a linear function. So let's set up the equation then, just like we would write the equation of a linear function. And let's start off with the items. So the items are going to be X. Okay, so we know that we can sell 2,000 items with a price of $10. And if we decrease the price by 25 cents, so if we go down to $9.75, we're going to sell 250 more. And I want to make a nice neat number here. Let's say we take the price all the way down to $9. So then what does that mean for the number of units we'll be able to sell? Well, it should be 3,000. So the number of units is going to be the x. The price is going to be our y. So the equation that we want to come up with is the price is equal to mx plus b. Okay, so let's find our slope then. So our slope is going to be 9 minus 10 over 3,000 minus 2,000. So negative 1 over 1,000. Then we want to find the y-intercept, so we take one of our points and plug it back in. Let's take the first one, price of $10. When we sell 2,000 items. So this will give us a negative 2, and so we're going to add 2 to the 10, so we get a y-intercept of a positive 12. So my equation becomes P is equal to negative 1/1000 x plus 12. Okay, so that's referred to as the demand function. Let's see, here's the demand function. So that demand function tells us what price we're going to get in terms of how many units we sell. All right, well, that's the demand function. Now let's find the revenue function. So remember we said in the last one that the revenue function is equal to the number of units sold times the price. Well, this is our price then, so our revenue function is x times this. Okay, and if we multiply that out, we would get a negative 1/1000 x squared plus 12x. Okay. So that's just the formula for the revenue. So if I asked you to find the marginal revenue, then what would you do? You would find the derivative of that function. Okay, so you will get lots and lots of practice of this on this next section when you come back to class. And same thing is going to be true then with marginal cost. So to find the marginal cost, it's going to be the derivative of the cost function. So then you have to set up the equation to get the cost. Okay, so hopefully you'll get used to it because we do a lot of these applications. We do them over and over again throughout the year. All right, see you in class.